Hi guys, in this video we're going to look at what is the Planck's law of black body radiation. So I think we had a small intro in one of the previous class what this is all about, and basically uh, there was a prior to this Planck's law of black body radiation, we had another law by the Rayleigh's principle. So in that we had a assumption that the spectrum of the black body radiation, which we already know, the sun spectrum is something of this sort, but the Rayleigh's law was somewhere right up to this point from the left part. Here we are what we are plotting is the spectral irradiance. We are plotting the spectral irradiance with respect to wavelength. So wavelength lambda. So the Rayleigh's law somehow had the conclusion that the spectral irradiance will keep on increasing as frequency increases, which means that as the frequency and the lambda increases to the right of this graph and frequency is just opposite, which means that this increases towards the left of the graph, and therefore you will get the as mu tends to infinity, and this had the principle that energy will also tend to infinity, but energy or the spectral irradiance will tend to infinity. But then it is practically observable that the solar spectrum that we are receiving, considering it as a black body, had a different graph. So this was derived by Rayleigh from the law of equipartition of energy, or the Maxwell-Boltzmann distribution of entities. So it had a concept that the energy distribution or the amount of energy distribution is continuous, but then Planck in 1900 brought the big discovery that that is not the case with the photons. With photons we can look at the energies as discrete amount of energies. The photons will have a discrete amount of energies, and he gave this equation of E is equal to n into h nu, where n can take values from 0, 1, 2, 3 up to n, and it is dependent, this energy is purely dependent on the frequency of the photon. That was one postulate that Planck had made, and he also gave the definitions that the mu is the natural frequency of the oscillating charge. So let's say the wall of the black body is radiating the energy, then the frequency of the radiation, electromagnetic wave, will be equal to the natural frequency of the oscillating charge itself. Natural frequency of the oscillating charge in the sense the charge of the wall, the charges of the wall, which is emitting the radiations. So let's say charge is oscillating, and therefore these oscillations are emitted out as radiations, so it will have the same frequency as the natural frequency of the oscillating charge. So that is what he postulated, and so that is one of the starting point of considering this photon as a particle, and it is we call it a quantum of energy, or you can also say that this was the major breakthrough which introduced the new field of science called the quantum mechanics. So here what we are going to do is that we are going to look at some of the equations, or you can say the derivation for spectral irradiance. So we'll be looking at how this derivation for the spectral irradiance is being made, or how we can derive this equation. So firstly what we have to look at is that we'll have to first, for finding the spectral irradiance, let's give this a function. Let's write it as a function, spectral irradiance. Basically it's a function of u of nu and temperature. In some other places you might find this, that the nu is replaced with lambda. It's all the same. There's not much difference. Basically there is only a small difference of nu is equal to c by lambda. So you can write it in any form, that's not a big deal. So what we first do is that we'll find what is the density of states. So density of states means that's the let's say what is the amount of photons that can occupy any state. So let's say it's similar to, let's say there is a auditorium and there are like thousands of seats. So how many seats can be occupied by a person, I mean the people. So there is a auditorium, or there is a density of states in any cavity. So how many states are there, and after finding the number of states, we'll multiply it with a probability distribution, or a distribution function, you can say. So we'll which means that how many states will be occupied, that's the distribution function. So the distribution function f of nu is actually the 1 by exponential of h nu minus mu by kt minus 1. This is the probability distribution of photons in these density of states. And then to find the spectral irradiance, you will have to multiply it with the energy of the photon, which is h nu. So this will be the final expression for our spectral irradiance. But then this is how we are going to derive what is the expression for spectral irradiance. So this is the basic idea with which we will start, and then we will find what is the density of states, and then we'll apply all these formulas and we'll find what is the spectral irradiance. So first, to find what is the density of states, or the number of states available, we'll first look at the Heisenberg's uncertainty principle. So the Heisenberg's uncertainty principle says that to differentiate two states, there should be a particle should have different position and momentum. So which is given by the equation delta p into delta x will be greater than or equal to the h, which is the Heisenberg's principle for a single dimension, for one dimension state. If you look at 3-dimension space, then this equation would turn out as delta px into delta py into delta pz into delta x into delta y into delta z is greater than or equal to h cube, or you can write it as equal to h cube. Then what we are going to do is that we look at the momentum space. So we will be looking specifically onto the momentum space, where we'll get the values delta px into delta py into delta pz is equal to h cube by, instead of x, y and z, since the position of electron, sorry, it's not an electron, the position of a photon cannot be specifically said inside a cavity, we'll have to take it as the length Lx, Ly and Lz of the cavities, because the position of the photon can be in any place and you cannot specifically say the photon is at which point, so we'll have to take the entire cavity or the volume. So we'll get this as Lx into Ly into Lz, and when we take it in this equation, we'll get it as, when we multiply all these things, we'll get it as the volume of the cavity. So basically we are looking at the density of states of a cavity so so you got the momentum space. So let's look at what is this momentum space. So yeah, so what we get is we get a cuboid with this is your delta. Let's take this as y, this as z, and this as x. Then we get this as delta py, this length, and this is delta pz, and this will be delta px. So this is a small cuboid, and this will be the what do you say, momentum space, or one momentum space you can say, and or one state, and you will have to find out how many such states we'll have to find out how many such states can exist in a sphere. So this is a cuboid which has the momentum space volume in this form, h cube by v, and which is delta px into delta py into delta pz. So the cuboid, and now what we are going to do is that we are going to look at a spherical a sphere. So let's say we are going to take a sphere in this fashion, and we are going to find how many such states. So this is one state, so this is one state, and we are going to find how many such states can exist in this sphere. So what we have to do is that we'll have to find what is the volume of the sphere, and then we'll have to divide it with the momentum space, or the volume of this momentum. So that is what we are going to do over here. So the radius of the sphere will also be taken as a momentum p. So that is because we are having a momentum space over here, and then we are going to divide it with the momentum space, the volume of the sphere. So again, the radius will also be in terms of momentum, and therefore what we get is that the number of states. So this is basically one state, therefore because we are taking a delta px, delta py and delta pz, so the number of states in this spherical volume can be written as the entire volume of the sphere. The volume, we know what is the volume of a sphere, which is 4 by 3 pi r cube, 4 by 3 pi r cube. So here instead of r, we have taken a momentum p as the radius, because we are looking at the momentum space. So 4 by 3 p cube will be the volume of the sphere, and then we will be dividing this with the volume of this one state to get the number of states. So that is going to be h cube by v. So we'll get it as Now this is the number of states, but then we know that we'll have to multiply it with a factor called the degeneracy factor. Which means that degeneracy factor. So what it means is that the light, let's say this is the direction of the propagation, so it has biaxial or two axes in which the light travels, and therefore in each state these have two axes of motion with different intensities. It is possible to have two axes of motion with different intensities. Therefore for each such state, basically photons of two different spins can be accommodated. So we'll have to multiply the number of states in the spherical volume into a factor that is 2, because there are two photons that can be accommodated, because they can have two different waves across the direction of its motion. So this degeneracy factor becomes 2 over here, and then we'll get this value as 8 pi into p cube by h cube into v. Now this v is the delta x into delta y into delta z. So in the normal space with position, or this is Lx into Ly into Lz. So when we look at the number of states per unit number of states per volume, we'll get this as we can divide the number of states here, this n divided by v. So this v comes out to here, and we'll get it as n by v is equal to 8 pi p cube by h cube. So that will be the in terms of the positional volume. So before we were looking at the momentum volume, and now we are looking at the positional volume. So we are dividing it with the positional volume. So you get the expression as sorry, there is this 3, yeah. So we'll get it as 8 pi into p cube by 3h. So this would be the number of states per unit volume. Now what we do is that we will look at the photons. So since we know that the light is always going in all directions, so and we have taken a sphere, what we are going to do is that we are going to find the number of photon states in a given solid angle. So this can be looked up as a sphere, the cavity, or so in this cavity, or if we take it as a sphere, let's say this is a surface, a small surface area on the surface of the sphere, and let's say this is the solid angle corresponding to it. So this is the solid angle. So we know that the solid angle is given as solid angle is given as area by radius square. So let's say if you want to get the same number of photons per unit solid angle, then we'll have to divide it with the entire solid angle of this entire sphere, which means that we'll have to take the entire surface area of this sphere. The entire surface area of the sphere is 4 pi r square divided by the r square. So r square and r square gets cancelled, and the entire solid angle of a sphere is basically 4 pi. So we'll have to divide this value with 4 pi in order to get the number of photon states in a given solid angle. So the number of photon states in a given solid angle. So we are taking any solid angle and we are going to look at what is the number of photon states in that particular solid angle. So that will be given as 8 pi into p cube by, we'll have to divide with this value 4 pi. So only then you will get the number of photon states in a given solid angle. So when you divide it with this 4 pi, you will get it as 3h cube. So 8 pi and 8 pi gets cancelled. You get 2, 4 and 8. When you get cancelled, you get it as 2. So 2 p cube by 3 h cube. That is what you get with this equation. And now we know that what the energy of photon, c, the velocity of the photon into the momentum of photon is equal to the energy h nu of the photon. So we know this if you multiply the momentum into the velocity of the photon, you'll basically get what is the energy of the photon. So this is a formula. If you check the dimensions also, you will be able to find that this is valid. This turns out to be the joules, and we from here we can write what is the formula for the momentum. So the formula for momentum turns out as P is equal to h nu by c. So we can substitute this form over here in this equation, and then you will get the form as 2 into h cube nu cube by 3 h cube c cube. So we can cancel these two terms. So we get it as 2 nu cube by 3 c cube is the number of photon states in a given solid angle. Right now what we're going to do is that we're going to find what is the density of states with respect to a small change in nu. So this is for a particular value of frequency of photon, but then what is the density of states, let's say d, for mu to mu plus delta mu. So that is the change number of states with small change in mu. So for finding that, what we can do is that we can do a small differentiation with respect to mu, this above expression. We'll do a partial differentiation with respect to mu, and we'll find out what is the change in density of states with respect to change in small change in the frequency mu. So what we get is that 2 mu cube by 3 c cube. Sorry, yeah. So when you partial differentiate this value, you get it as 2 into 3 mu square divided by 3 c cube. So as 3 and 3 gets cancelled, you get it as 2 mu square by c cube will be the density of states. The density of states with respect to change in a small value of mu. So now we have found what is the density of states with respect to a small change in mu. Now we can write what will be the spectral irradiance. So spectral irradiance will be now mu and temperature as a function of mu and temperature. You can substitute this value over here for the density of states. So you will get it as 2 mu square by c cube into 1 by exponential of h nu minus mu by kT minus 1 into h nu, the energy of a photon. Now here this mu is the chemical potential of a photon. So the chemical potential of photon, which is 0. So you can neglect this term and you will get it as you will take this h and nu to the this over here, you get it as 2 h mu cube by c cube into 1 by exponential of h nu by kT minus 1. So this is the expression for the spectral irradiance of photons, and this this was the derivation that was done by the Max Planck, and basically this expression was further used by many other scientists also, like Einstein and others, to explain photoelectric effect and all the other phenomena. So this also confirmed that what we saw in the beginning as E is equal to nh nu shows that the energy of photon as nh nu is a function of mu, as well as these are discrete packets of energy, and they have the particle behavior as well, so which was thrown away at some point, only considering that the light has only the wave nature and not the particle nature, but which came back into existence with Planck bringing up this new equation for the energy. And this is the equation for the spectral irradiance, that we looked at with the solar spectrum. So this is the what you say, the spectral solar spectrum with respect to the spectral irradiance and wavelength lambda. So the Planck was perfectly able to explain this phenomena that the spectral irradiance tends to 0 at frequency tends to infinity. At this point, this was coming back to 0 when frequency was tending to infinity. So this couldn't be explained before this particular experiment, but this was the major breakthrough Planck was able to bring about with this with his experiments and with his derivations. So guys, I hope you guys understood what we have discussed in this class, and we'll meet in the next class.